All right, guys, good afternoon. Welcome back. Just another couple minutes, basically, and then we'll resume with part 2 of this lecture series on Chapter 12. Hope you're all doing really good, and it's good to be with you. Feel free to say hi or anything else. And sorry. And in just a minute, we'll be ready to go. Hey, Edward, Nancy, Danny. Ellie, Danny, Vanessa. Welcome, everyone. Margarito, Megan, Emily, Alexa, Nick. Cool. Hey, Micah. Hey, Mick, Diego, Brenda. Welcome, everyone. Chelsea, Cecilia. Okay, guys, so here we go. Let's get started. It's 1 p.m. Thanks again for being here. Today, as you may know, if you're just following our calendar of dates and you've been attending, you'll know that today we have the second installment of our lecture on Chapter 12, which has to do with science. And so we'll wrap that up today. We'll finish all those notes on Chapter 12. And then what you have to look forward to on Monday coming up, next class period, will be the third quiz for this class. So that third quiz is just on Chapter 12. It's all about science and this information that we're talking about this week. Also, just to keep in mind, the third quiz is worth a little more than the first two. That's all included in the syllabus, but the first two quizzes are each worth 5% of the grade, and the third, since it's the last one, is worth 10%. So your other two quizzes, the first one on logic and argument was 50 points, and the second one on fallacies was out of 50 points, but this one that's coming up, it'll be scored out of 50, but then I'll just double the point value, so it's really out of 100. After this, after the third quiz that you have, I'll be assigning one more homework assignment. So you have a last homework assignment, and then it'll just be the final exam. Don't forget also that your third homework assignment is going to be due to me by tomorrow night, by midnight. So you still have another day or so to work on it, but don't forget that one. That's the fallacy advertisement assignment. So make sure to get that one in before the end of the day tomorrow. I had a few students asking a couple questions, which was nice. But if you do have any such questions, you can let me know anytime. Otherwise, just make sure to send me your document with all the examples and explanations anytime before the end of the day tomorrow. Okay, so if that's all clear, just kind of making sure that that's all clear and detailed, then I'll just continue with Chapter 12. But as usual, if you have questions, comments, reactions to anything, just put them in this chat or email me anytime, and we'll just take them as they come. Okay, so good to see you guys. Like I said, let's pick up where we left off then. So we were talking about science. That's Chapter 12 and the topic of Chapter 12. So just a couple of brief things about what we covered on Monday. We started by giving this general definition of the concept of science. That is reasoning from observable facts to testable explanations for the facts. So in science, we obviously observe the world and what happens in it, but we don't stop there. We want to try and give explanations for these observed facts. The explanations that science gives are supposed to be capable of being tested for their truth and accuracy. So we give testable explanations for observed facts. That's how science works. Science is all about explaining the reasons that things happen. Why does lightning happen? Why does a volcano erupt? Why does the sun rise and set in the sky, etc.? So science gives us explanations for such questions that we could give experimental confirmation for. And we talked about some important figures in the early history of Western science. For example, Nicholas Copernicus, who discovered the heliocentric model of the solar system, which replaced the older geocentric model. That is the notion that the sun is at the center of our local cosmos. He discovers this using new telescopes that were then coming into use. Prior to his discovery, geocentrism was the prevailing dominant opinion, and that was because of deference to the church, which thought that God would not have put the planet Earth with human beings in a random, non-central position. After Copernicus, we talked about Sir Francis Bacon. His major legacy was to have created the scientific method and systematized the different steps of the scientific method, where we begin with observation, hypothesis, and eventually testing and experimenting. Afterwards, we talked about what are some basic assumptions of science, and I mentioned a couple that are in the book. One assumption of science is empiricism, the view that most human knowledge does come from the five senses and what we can observe by using the five senses. Another assumption of science is the assumption called objectivity. This is the belief that we can come to learn about reality as it really is. We can learn about the universe as it really is, not just as it seems to be or appears to be. That we can get to the objective truth of things and that we can do so with no bias. Science believes that we can discover actual objective truth, not just personal opinions or feelings about things. And so then we talked about the assumption of materialism. Can anybody tell me what that one means? Just a quick check with you. Materialism, as defined in our book and in this chapter, means what? What's the belief of materialism? An assumption of science, a basic assumption of science. What is that? It has to do with what everything is made out of. That's a little hint, but you can tell me the rest. Who knows that one? Materialism, definition, what is that one? Okay, very good, Danny. That everything in the universe is made out of physical matter. Yes? One more little extra item of info to add to that. Yes, it says everything in the universe is made out of physical matter. Even what? Even us, that's right, including us and our consciousness. So human consciousness, the ability to think, feel, perceive, your ability to introspect and have a mental life, all of that stuff is also just made out of matter at the end of the day, according to physicalism, materialism. What's physical matter? It's anything that is extended in space, and the most small particle of that is often referred to as the atom. So according to materialism, we're all made out of atoms, and everything else is. It's just put atoms together in specific kinds of ways, and you get these objects that you see, including even human beings. So it would be a denial, for example, that there is anything non-physical or supernatural having to do with consciousness. It would deny, for example, the concept of the afterlife or the soul, because it would be some kind of idea of consciousness that doesn't reside within a physical system. And that's claimed as impossible by materialism. Okay, another assumption of science is predictability. This assumption is the idea that the whole universe is orderly and predictable, which means that if we have established certain cause-effect relationships in nature, that those will be permanent, stable, that they will be repeatable, and that they would hold forever. So one example I mentioned was just the concept of gravity. You already know, I guess, that if I release this marker, it's not going to fly away or just stay floating, but that it will fall. And why do you know that? Because we think that the law of gravity is not just a temporary phenomenon that takes a break or decides to just stop doing its thing today. That gravity will work not just yesterday or right now, but forever into the future, even though we haven't been in the future yet. So it's an assumption, isn't it, that these laws of nature are permanent in the way that they always apply to the facts and that they will never change or alter. Okay, hi Yvonne, good to see you. Unity is one more assumption of science that was discussed. That's the assumption that the universe overall is unified, meaning that there will eventually be one single set of scientific laws that could explain everything, from the biggest to the smallest phenomena. We hope to someday get there. As of today, we've not yet quite achieved this, major goal of science, because we have both quantum physics and relativity, which have some discrepancies at the margins. But ultimately, scientists do think that we'll get a grand unified theory that will make it possible to explain the occurrence of all events. Okay, after that, we talked briefly about what are some limitations of science. I talked to you about how one limitation is that science assumes that the external world exists, which I guess we can't absolutely prove, according to Descartes and some others. Science also can only study that which is observable. So if there are things which are not observable, then they would never be capable of scientific analysis. And some people also criticize the idea of predictability, which scientists assume. How can you really know that natural laws will never change in the future? It seems like it's assumption that we make, but how can we prove it? Now, after that, we talked about 4 different attitudes that people can have about the relationship between science and religion. Does anybody remember what some of those different views were? Just to complete this quick crash course of summary from the material of Monday. Different views, attitudes, perspectives that people have concerning the relationship of science and religion. What are some of those views, if you know? Like, some people think that when it comes to science and religion, if they come into conflict, some people would say what if that happened? Let me just get that one from you. Just checking in. Yeah, science and religion, anybody? Views that people have about their relationship? What are some of them? It just takes a minute to think, to go to the notes, to type, but you'll do it. Okay, so here we go. Danny, no, not Danny, rather Dimitri. Science takes priority over religion when the two conflict. Yes, that is one option. Some people will say that if science and religion disagree about something, then it must be science that's actually correct. Another view, good Chelsea, is that science and religion do not disagree. They're actually compatible. Maybe if we interpret the scripture the right way, we'll see that it doesn't even say anything different from the scientists. Like maybe if it says that the universe was created in 7 days, a day means something more than 24 hours. Also, Chelsea, that science and religion deal with different topics. Correct, that's another view. Some people think that science and religion are in their own separate lanes, that they have their own material that they're focused on, but not the material of the other side. So some think that science is all about the physical world and the objective study of cause and effect relationships, whereas religion is more about the moral side of life and your subjective spiritual side. So that's another idea that they're dealing with different topics. What's the last one? So there's 3 that I've seen here. Science takes priority, science and religion are compatible, or they deal with different topics, but also let's not forget the one other option, actually a quite popular option with many people. And what is this other? You'll tell me one last one. That's right also, Chelsea, that religion takes priority over science when the two conflict. So like Dimitri, the reverse of yours is another option too. To say that when science and religion don't agree, like say evolution versus creationism, if a person holds that other view that religion takes priority, they'll go and say creationism is correct, evolution is false. So those are 4 different ways that people can approach the tensions and contradictions that exist between science and religion. Either reject religion if there's a contradiction between the two, reject science, suppose that they're not even talking about the same stuff, or that they really do agree in the end. Okay, now that brings us back to where we were at. So now we can continue with the remaining notes of chapter 12 from here. I just wanted to always kind of get us back into the subject by doing a little review to start the meeting. Okay, so the next thing that the book talks about in chapter 12 is the different steps of the scientific method. So we're going to go over those steps. But before we do it, I want to show you something which is also mentioned here in the book about how the steps of the scientific method have some very rough similarities to the processes, the steps in critical thinking. Okay, so similarities between the scientific method and critical thinking process. Okay, so you may remember that way back when we started in the class, chapter 1, we talked a little bit about how critical thinking could be seen as a process that plays out in three stages, 3 steps. So maybe someone will remember those steps. There is experience, the first step of critical thinking. That's just when you say what happened, without yet trying to explain why or how. Okay, so critical thinking, let me create two little diagrams here. Critical thinking process versus scientific method. And we're trying to show that there are some basic similarities here. So with critical thinking process, if you may remember, we go from experience to interpretation, and then to the step they call analysis. Okay, so like just a quick review of that. Experience, as I said, when you just say what the thing was, what happened, without yet trying to explain why or how. Like I got fired from my job, or I got an F on my exam, or whatever. The experience is just what happened. But when you go on to the next step, you're trying to give the explanation of why. Why did I get fired? Why did I get a bad grade? Maybe it's because my coworkers told lies about me, or maybe it's because my professor doesn't like people who look like me or something, right? You got your explanation. But then eventually you'll go back, you'll analyze your interpretation, and you'll question it. You'll say, is there a different interpretation that's more reasonable than the one I had at first? Maybe sometimes your first interpretation is a little biased or a little bit clouded by emotional factors or whatever. So sometimes your later analysis will be a little bit more accurate and reasonable than the initial interpretation. Okay, now in the scientific method, there are more than just 3 steps, as we're going to show, and we're going to fully line up what all those steps are. But in general, if we wanted to point out the 3 main steps of the scientific method, we have these. We have observation, where you just observe a phenomenon in the world, and then hypothesis, which is when you try to explain what's the reason that the observed phenomena happened. Okay, so like you see a lightning flash in the sky, and let's say you don't know what's causing that. This is like an earlier generation of human beings. So you create a hypothesis. Maybe it's caused by the effect of water on the surface of the earth firing bolts of lightning up into the sky when the water gets too dirty or something. You know, just a really weird off-base explanation. But in a hypothesis, it's not yet tested. It's just an initial educated guess to try and explain the observed phenomenon. But you don't stop with the hypothesis. You eventually have to give an experiment which will test that hypothesis. And the experiment can either confirm it or it can show that it was not correct. Now, look at how an experiment tries to question the hypothesis as to whether it's verifying it or disconfirming it. In the same way, when you analyze your previous interpretation of an experience, you're going to either verify the initial interpretation or you're going to replace it with a different one. So analysis checks on the accuracy of the interpretation, and experiment checks on the correctness of a hypothesis. So there's similarities here because in both cases we're trying to explain why an event happens. In everyday life, we just call it critical thinking. Events happen, we experience them, we try to interpret the reasons, and we allow ourselves further analysis into the future. In the scientific method, in a similar way, we begin by observing data and facts. We create hypotheses which try to explain why they happened, and then we have to test that hypothesis to see whether or not the test will prove or disprove that it's true. Now, having gone over those basic similarities, now we're going to go through each and every step of the scientific method in more specific detail. So here we go, the scientific method. As we discussed earlier, the steps of the scientific method were initially described by the philosopher and statesman Sir Francis Bacon, the British citizen from the 17th century. Okay, now the first step, identifying the problem. Okay, at this stage, the first stage, you just observe the world and you identify some unexplained phenomena, something that is happening that you don't yet know how or why. So observe the world. So the so-called problem is the question, why or how does this event happen? So without a event to explain, there's nothing for science to do, right? Science has to be able to explain how or why things happen. So of course we need to begin the process by pointing towards something in the world that we need to explain. So what could some of these problems be? I don't know. As one example, right now on this planet, we're seeing a major decline in the number of honeybees that there are globally. This has even been labeled the bee colony collapse disorder. And there's not 100% agreement as to why that's happening. So that is something that we have to explain, or we would like to know why it's happening. But suppose that the first step we could just say is identifying this event. Bees are dying off. That's something we want to explain. But science doesn't just stop by noticing that this event is happening. We next try to generate some explanation. So that takes us into the second step. I gave you this random example of bees, but again, as you know, in science, it could be anything. Like, why is it that the volcano goes off, or the lightning bolts appear, or why is it that I don't know, the bird is collecting pollen, or the mating behavior of certain animals? Why is this the behavior that we see? So anyway, when you see things happening in the world, scientists try to explain them. The second step will be to develop an initial hypothesis. That's easy to read. Hypothesis. Okay, so develop an initial hypothesis. So you want to provide an educated scientific guess to explain the occurrence of the problem or phenomenon. So what is a hypothesis? It is this. It is an educated scientific guess to explain the observed phenomena. Or if you want to use the term problem, you can call it problem/problem. Okay, so develop an initial hypothesis. Step 2. You've got a problem on the table. Now the work is, why did that happen, or what's the reason that happens? So you try to develop an initial hypothesis. What is that? It's an initial educated scientific guess to explain the occurrence of this phenomena or event. If it was bee colony collapse disorder, maybe people will give different initial hypotheses. Maybe one person's hypothesis is, well, we see this kind of bee colony collapse happening at around the same time as cell phone technology is widely proliferating. Could it be that cell phone tower radiation is somehow interfering with the life cycle or migratory patterns or something of these bees? Maybe that's the explanation. So that could be like a hypothesis. It's just an attempt to try and explain what could be the reason. Maybe there are other possible explanations. A different hypothesis could be that due to the warming trend of the planet over the last 30 or 40 years, it's affecting the lifespan or physiological features of some of these bees, making them less successful at mating and reproduction. I don't know. I'm just suggesting possible hypotheses that could be used in an effort to explain the given example, okay? So anyway, at first these hypotheses are tentative, and they can be changed later if you find that they're not the best formulation of the explanation. There's a difference between a hypothesis and a theory, by the way. A hypothesis is an educated scientific guess to explain the observed phenomena, and a hypothesis kind of graduates to the status of theory when it becomes very well tested and well confirmed. Okay, so just so we know that, this little sidebar in the middle of this list of scientific method steps, but let me just make it clear to you that a theory is just a very well proven, a well-proven, well-confirmed hypothesis. So the theory starts off as a hypothesis, and if it gets experimentally verified over and over again by a whole bunch of people in different conditions, then we would say it has attained the status of a theory, and a theory is something that we regard as like the closest approach to objective truth in science. Notice this, that science, by the way, never makes the claim that these hypotheses or theories cannot be contradicted. They never say it's absolutely certain, because science is about inductive reasoning. And with induction, all we get is that the conclusion is very, very probable based on the collected premises. So hypotheses and theories, we think that we have the truth, but we never say that there's no possibility that we might have to revise the theory later in the light of future information. So science is always subject to revision if new information comes forward that contradicts an established explanation. Okay, so anyway, guys, here's where we're at. Identify the problem, figure out something that you have to explain that, of course, has not yet been explained. Develop an initial hypothesis. This is going to be your first stab at trying to give that educated scientific guess that will explain why the thing has happened. And then we go on to the third step. Okay, so the third step of the same method here would be to gather additional information or data and refine the hypothesis if needed. Okay, so all this has to do with is the following. Sometimes as you've now developed a hypothesis and you're starting to collect information and data on the connection between the hypothesis and the phenomena you're trying to explain, sometimes that will require you to make slight edits, alterations, little tweaks to your initial hypothesis, and then it gets into its final form. So make any adjustments to the hypothesis as necessary based on your initial data collection. So okay, so like here, I'll give you a little example. Suppose that someone's looking at the outbreak of mass shootings and school shootings in the United States in the last, I don't know, 20 years or so. Because there's a lot more of them that have happened over that span of time than in the, let's say, 20 years prior to that. So that's a problem to explain. What's causing all these shootings? Why are they happening? Suppose that someone has this hypothesis and they say, well, I think it might have to do with all the very sophisticated video games that people have started playing in that same time frame. So maybe because there's more realistic games and stuff, they're causing people to want to take violent actions more. But then they start to collect initial data, and they notice that there are video games being played in all kinds of major countries and cities across the world, but not the same phenomenon of mass shootings are seen in all those places. So maybe that causes the person to revise their theory a little bit. Maybe it has to do not just with video games in general, but only specific genres of games, like first-person shooter games or something. So they modify and tweak the hypothesis, make it a little more narrow. I don't know. Here's another example that's just off the top of my head. There's been some data to suggest that young people in this current Gen Z kind of generation, there's higher rates of depression, suicide, and stuff like that. So problems with mental health. And I mean, there's any number of reasons that you could imagine that are causing that, but that seems to be a problem, something to be explained. Why is there higher rates of suicide and depression in the current group of young people than, let's say, I don't know, millennials, Gen X, and so forth, baby boomers? One might argue, okay, well, is it perhaps because of social media? Everyone's, comparing themselves against others on social media. That's kind of a relatively recent historical phenomenon, the existence of these kind of social media websites and things. Could this be driving up teen and youth depression rates? But suppose that someone looks at that and then they start to actually study the issue to see if there is any kind of link. And they noticed that it happens more in common cases where someone's using like photo sharing websites like Instagram rather than just text like Facebook or Twitter. So now they refined their hypothesis so that it's not that the existence of social media is driving up suicide rates in the youth, but rather maybe ostentatious displays of beauty and wealth and status that you see in social media sites like those. Anyway, all I'm saying is that sometimes that initial hypothesis has to be slightly modified after you collect some initial data and you see that it requires a little revision. After that, though, you're good to go, and now you can move on to the all-important fourth step. The fourth step is one of the big ones of all, and that is the experimental step, the test phase. So now, step 4, simply test the hypothesis. So what is this? Testing the hypothesis is when you, in a real world or laboratory setting, you conduct an experiment. And this experiment will either confirm or disconfirm the hypothesis. So it could have one of two outcomes. Anyway, so either in a real world or laboratory setting, one conducts an experiment that will either confirm or disconfirm the hypothesis. Okay, so whether it's in the real world or in a lab, you're going to conduct an experiment, and that will either confirm or disconfirm your hypothesis. So with the experiment, you put the hypothesis to the test. Let's go back to this question I had earlier, imagining the example of bee colony collapse disorder. So rising number of bees on the decline globally. It's actually, I mean, the situation I'm referring to here with the bees, it's not even limited to bees. I've been reading some more recent studies that say that there's a wider concern about the loss of all kinds of insect species in nature. And that could have all kinds of significant impacts on the food chain and the ecosystem. But anyway, limiting ourselves to bees for the moment. Suppose the question is, why are they all dying off in such great numbers right now? And someone's hypothesis was, I don't know, maybe it has to do with the development of widespread cell phone radiation and cell phone towers. So if somebody thought that it is cell phone tower radiation that's causing the bees to die off, then they might have to, based on that hypothesis, conduct an experiment. You can't just say, hey, here's my hypothesis, so that's the truth. You have to test it. And the test may not verify it. So this is a critical stage in the process. How do you think we might test this question? We have to have some kind of ability to control variables, right? So we have to be able to see whether or not the suggested variable is the thing that's the causal factor that causes the phenomena. So how, for example, do you think this question could be tested? The question is, are bees dying off because of cell phone tower radiation exposure? What do you think? I'm asking you, put in the chat if you can. Just dream up the parameters for designing this experiment. So how do you think we could conduct that test? How can we test whether it's cell phone tower radiation? Just kind of walking you through one concrete example so that it's a little bit more real to you. So in this case, what might be the way of testing that? Just taking a second. It's okay. But let me know. We heard the question, right? But yeah, just go ahead and hit me with your answer whenever you're ready. Go ahead, fire away. Nothing but time, so just let me know. Question of, how would you test it? Okay, Brenda, have a control group of bees that are not around the technology, yes. And then another group that is. And if your hypothesis is correct, then you should expect that the control group, which has been exposed to this radiation, you should see them die off in greater numbers than the other group that's not similarly exposed. So take a population of bees, right? Pump them full of, in a sequestered environment, a bunch of this cell phone tower radiation. Have another isolated group that's prevented from any such exposure. And if the hypothesis is correct, then we should see some detrimental impact on the control group that's exposed to the cell phone tower radiation. Now, what would count as confirmation for your hypothesis would be that afterwards, what you observe as the results of the experiment are, yeah, that group is dying off in much greater numbers, and the other group is doing fine. Then that would give verification for your hypothesis, right? On the other hand, maybe you do this, we run this experiment, and there's no measurable difference. The group that's getting hit with a bunch of cell phone radiation is not even dying off at all, or there's no statistically significant difference between what's happening with them and the other group that's not affected by the same thing. So then, the experiment would show that your hypothesis was not correct. And that's possible. We have to run the test so that we can find out whether it was the right explanation or not. Well, that leaves us with one more step in the end, okay? The last step is simply to evaluate the hypothesis based on the based on the test results. So that's step 5. Okay, so if the experiment confirms the hypothesis, so there's 2 outcomes that are possible. You can get confirmation or disconfirmation from the test. Suppose that the test does confirm your hypothesis. If so, great. Then you would publish the work and forward it to the scientific community so that others can replicate the same findings. Okay, so if the experiment confirms the hypothesis, then publish the results so that the scientific community can replicate them. On the other hand, if the experiment disconfirms the hypothesis, which is the other possible outcome, then, okay, and I'm going to ask you a question before I write the rest. If you run the experiment and it does not confirm your hypothesis, then you've got to go back in the method to an earlier step. Which prior step do you think this sends you back to if you don't get confirmation from the experiment? You go back to which step of the method? Just think about it logically, right? So you tested a hypothesis, but that hypothesis was not verified by the test. So now you must go back to which point? You get pinged back to which earlier step in the scientific method if you don't receive confirmation from the experiment. Now you got to do what? So, yes, that's right, Brenda. You would go back to the second step and develop another hypothesis, because you don't go back to step 1 and find a different problem because you still have the same phenomena that is yet to be explained. So you're still trying to discover the correct explanation for the observed phenomena, which means that you must go back to the earlier step 2 and develop, well, now it won't be an initial hypothesis because initial means first, but you go back and return to the process of developing a new hypothesis. And then you would run it through the remaining steps again until eventually you get a hypothesis that is confirmed by the experiment, okay? So if the experiment disconfirms the hypothesis, then develop a new hypothesis and repeat the steps. Okay, so there you go. Last step, evaluating the hypothesis based on the test results. You've got your results. Did they confirm your hypothesis? If so, it looks like this is a viable hypothesis that may be on its way to becoming a theory. So now you would publish the results of your study, and the remaining members of the scientific community will try to duplicate your results. So you ran an experiment in a lab or a real-world setting. It verifies your hypothesis. You publish these findings. Now other people in different research settings are going to run similar experiments. And if they can verify it in their work, then that adds further confirmation. And so a bunch of different scientists working independently, applying experiment to the same hypothesis, all getting confirmation, makes us think that this is the right explanation for that observed phenomenon. On the other hand, suppose you do an experiment and it does not show that your hypothesis was true. Like I said before, you expose a certain control group of bees to the given radiation, no effect is measured, so that did not show that it's probably the cause of their declining numbers. Then in that case, you would say, well, I did not have the right explanation, so it's back to the drawing board, as it were, back to step 2, develop another hypothesis and run through those steps again. Okay, so this methodology is the way that we explain events in the world. It's how we develop technologies. It's how we develop medicines. And so it's obviously a huge tool, perhaps the primary tool of humanity, to master and subdue the environment around us, to suit it to our needs and interests, and to make our lives better, healthier, and more productive. So we owe a lot of gratitude, I think, to the scientific community and for the process of science itself. Now, after this, we talked about, or we will talk about in chapter 12, what are some qualities of a good scientific theory? Okay, what are qualities of a good scientific theory? Because not all theories are equal, some are better than others. That means that we want to be able to distinguish between those that are good theories and those that are bad. What are the hallmark features, qualities of good scientific hypotheses or theories? So, qualities of a good scientific theory / hypothesis. Okay. Okay, so one of these qualities is relevance. So relevance to the problem being studied. Okay, so one very fundamental quality that a good theory or hypothesis has to have is it has to be at least relatable to the problem that you're trying to explain. Sometimes people give wild hypotheses and theories that are totally irrelevant to the subject that they're trying to investigate. Like if somebody told you, look, I think there's a lot of hurricanes happening right now because the divorce rate has increased a lot over the last 50 years. So the last 50 years, hurricane season has become more extreme. Also over the last 50 years, a lot more people getting divorced. The two things are correlated, so I think that's the cause. If people stop getting divorced, maybe we're going to have less hurricanes. Obviously, though, you could write that one off right away because a social fact about like people making up and breaking up cannot really relate to or have any connection to meteorological phenomena having to do with weather. So perhaps that would be one poor hypothesis on the basis that it's not really relevant. It's a social fact as compared with weather data. And that means that it's something that you should just write on. Another quality of a good scientific theory is to be consistent with other well-established theories. So consistency with other well-established theories. Okay, so I'll give you a little brief description or definition of that. Consistency with other well-established theories means this. A good scientific theory or hypothesis will fit in with and will not contradict others that have already been well proven in the past. So a good scientific fit in with and not contradict other well-proven theories. So I'll just highlight a couple of important key terms here. If it's a good scientific theory, it will fit in with, and it will not contradict other well-proven theories. Okay, so think about science in a weird way as like a big jigsaw puzzle. All the pieces fit together. And so a good scientific theory is supposed to arrive on this scene and fit into the patchwork of what's already been laid out before. If a new theory appears and it would force us to reject things that we think we've already proven pretty well, then that might not be the best theory because they're all supposed to build on each other. There's a saying in science sometimes that when we're working in the modern day, we're standing on the shoulders of giants that have come from before us. So the body of scientific knowledge is supposed to stack up and build on what's already been there before. It's not supposed to clear away all the old stuff with each new generation and just reject it. Now, of course, there are some exceptions to that. Sometimes a theory is truly revolutionary. If it has overwhelming evidence behind it, then sometimes it can cause us to have a paradigm shift and to reject things that we thought of earlier. In one case, we can imagine Einstein's theories of relativity are kind of like a paradigm shift away from Newton. But in the ordinary course, unless it is a revolutionary theory like that, for the most part, they're all supposed to cohere together and to fit in and not contradict each other. So suppose that I was telling you that my theory of how I got presents on Christmas was that Santa delivered them to me because he has the sleigh that can travel through the whole world on Christmas Eve and deliver gifts to people. For me to believe in that, I would have to reject all kinds of other very well-proven things that I've learned in science, like, for example, the mechanism of his sleigh propelling in the air. There's no known mechanism that could support that because it's driven by reindeer, which are terrestrial animals. So this would violate everything we think we know about aerodynamics and the biological facts that we think we know about reindeer. Also, how is he possibly able to store all of these items in one bag? This bag would violate principles of, the density of matter, etc. So for us to accept the Santa hypothesis for how my gifts come to me, I have to throw out all kinds of other extremely solid, well-proven stuff. So that's why it's not the best hypothesis. I'm kind of using a sort of a silly example, but in reality, there's all kinds of more robust and technical scientific examples of the same thing. So when a new theory emerges and it forces the rejection of others, that's a sign in some cases that it's not the best theory out there. Let me read from the book a little bit and point out the way it's described the same questions or topics. It says, science is a system of logically consistent hypotheses or theories. Scientific explanations are preferred if they are consistent with well-established theories in the field. For example, the hypothesis that internal processes in the ocean, such as the release of oceanic methane hydrate deposits, are the primary cause of global warming is considered a good hypothesis by environmental scientists since it is consistent with the established paradigm that global warming is a result of man-made and natural changes in the Earth. The intelligent design theory, on the other hand, does not meet this criteria because it is inconsistent with the theory of evolution. So if we have a claim in science that runs contrary to all kinds of other things that have been well established, that singles it out for skepticism as perhaps not a good theory. Okay then, so relevance to the problem being studied, consistency with other well-established theories. What's another quality of good scientific theories or hypotheses? Let's add to the list. So after this, we have what's called simplicity. And simplicity, I'll put in parentheses below, because this is also sometimes referred to in scientific terminology as the concept of Occam's razor. Get his name right, Occam's razor. Let me explain the concept then, and I'll go back to Occam in a minute. But simplicity is this idea that if you have two different explanations of the same event or phenomena, then whichever of the two is the simpler one, the one that involves fewer assumptions, is likelier to be true. Okay, so the simpler of two explanations for an event is likelier to be true. Simpler out of two explanations is the one that is likelier to be true. This is called Occam's razor in some circles because there is a medieval philosopher named William of Occam, and he proposed this idea. So his namesake is still mentioned sometimes in discussions of it, Occam's razor, or just simplicity. So let me explain with some examples. Suppose that one thing has happened, and a person is trying to reason and speculate as to why. Let's say that this person has parked their car, and then they go into a building of whatever kind. Coming back out to get to their car and drive off, they notice the car's not there in the parking spot. So that's a problem. And now they're like a little miniature scientific reasoner, trying to give a hypothesis. What's the reason for this, that my car is not there? Now, what is one possible hypothesis that you could imagine? Suppose that happened to you. I don't know if it has or hasn't. One time it did happen to me. My car was not in the lot, and I realized that it had been towed, but setting that aside, what's one explanation? What could be the reason that's not there, where you parked it? I know there's a range of possible options, but what might be one reasonable assessment of the reason? And this will help me explain this in a little more depth, so asking you for that. Okay, so Yvonne, you say towed for parking violation or maybe car theft. Those are different hypotheses, but they're both viable enough. You know, that could be the reason. Maybe I parked in a designated area where I was not allowed to be, causing the car to be towed. That's why it's not here. Or maybe the car was fine in its parking space, but someone was able to steal it, and that's what caused it. Brenda, you say maybe you forgot where you originally parked. That's also a possibility. So now I'm just going to pick two possible hypotheses and pin them against each other, and I'm going to ask you which one you think is the simpler and therefore the likelier to be true. Okay, hypothesis number one. I parked in a marked designated stall, and that was a violation, therefore it was towed away. And it's at the lot where the tow truck takes it. That's one place, possibly. One hypothesis, therefore, is towing. Here's another hypothesis. The aliens came down from outer space and abducted my car, and they're taking it away in their spaceship to examine it as a piece of human technology. Okay, so you heard the two hypotheses. Towed away by a towing company or beamed away by space aliens. Now, these are two attempts to explain. I mean, they are two hypotheses, I guess. But if you had to choose, which one would you say is a little simpler and more straightforward? The alien abduction or the tow truck hypothesis for the car not being there? If you had to choose. I mean, I think there's a clear winner here in terms of which one is simpler, but you'll let me know. Which one is the simpler hypothesis? That's not too bad to ask. Towed, exactly, of course, right? Because, let's go over it. To sustain the alternative hypothesis of alien abduction, we have to make all kinds of extra assumptions that we don't have to make when it comes to just assuming that the towing is the right explanation. So what other things do we have to assume to support this alien abduction hypothesis? What things do we have to assume that we don't know if that was to be true? And none of these assumptions have to be made with the other straightforward towing hypothesis. So, you know, humor me if you will. If it's aliens that took it, we would have to assume, for example, run out and tell me some of those things. You have to assume, first of all, aliens exist, which is not definitively known. So that's a big, heavy assumption. Not only would you have to assume that they exist, but furthermore, you'd have to assume that, yes, they exist, but also they care about my car for some reason. Like, of all the things that they want to examine, they want to take a look at my particular automobile for whatever reason. And then you'd also have to assume not just that there's aliens that exist that have an interest in my car, but that these existing aliens have the mechanism to transport themselves from whatever part of the universe they live in to the planet Earth. And I mean, that would mean that they'd have to be extraordinarily intelligent and advanced, because as you know, even humans, as smart as we are, we can't go to another solar system. The closest star is Alpha Centauri, away from our sun, and that you would have to be traveling at the speed of light for like 4 years to even make it to the next star. So what I'm saying is you'd have to assume that they're a very highly advanced civilization of aliens and they care about your car. But none of those weird and wild assumptions have to be built into the other idea that it's just towed. Now, Occam's razor and the simplicity principle just says that that's generally the case, not just with my funny example here, but overall, when you have two competing explanations for a single event, the one that includes fewer assumptions is the one that's judged to be likelier to be true, because the universe, they say, is elegant and parsimonious, so it favors the simpler explanations which have fewer assumptions built in. That's why, for example, conspiracy theories are often regarded as a violation of Occam's razor, because whenever you have a conspiracy theory, it tells you that the official account is false. And the conspiracy theory is usually something much weirder, and it requires many additional assumptions of things that you don't know, that you don't have to assume by taking the more straightforward mainstream account of the events. Let me read something from the book about the same, and you can connect that to the discussion in class. So it says here, if two hypotheses or explanations both satisfy the basic criteria, scientists generally accept the one that is simpler, a logical principle known as Occam's razor. The great majority of scientists reject intelligent design theory because, among other reasons, the theory of evolution is simpler than that of intelligent design. Because if you assume that God creates things with his intention behind it, then you have to assume the existence of the supernatural creator and that he has a relation to the natural universe, which is mysterious. But none of those things have to be assumed on the evolution hypothesis. And it says that the process of evolution, scientists argue, can explain the gradual development of complex things such as the human eye. There's no need to add the idea of an intelligent designer to the process. Okay, so just a few more additional examples from the book and some summary of the point mentioned on simplicity. All right, so then next we just have a couple more. Another quality of a good scientific theory or hypothesis is what's called falsifiability. Falsifiability. So here's the idea. A good scientific theory is capable of being proven false. Okay? Okay, now you might look at that and think, isn't that strange though? How can it be good if it can be proven false? I thought the whole point was to prove that it's true. Yes. Able to be proven false does not mean that it is proven false. It just means that in theory, we have a way of testing whether it's false or not. Okay, so a theory or a hypothesis is not scientific if there's no way of disconfirming it, if there's no way of falsifying it. Because if you don't know what would indicate that it is false, then you also cannot test whether it is true. Okay, so like in the example that I gave you, where I said, hey, our bees may be dying because of cell phone radiation, and that's a hypothesis. Well, that hypothesis can be falsified. What would falsify it? In exactly what we discussed earlier. If you conducted an experiment which exposes a population of bees to that phenomena, and the expected effect does not occur, that would give disconfirmation to the hypothesis. So we know what would count as an instance of falsification. That's how we're able to test for it. How can we test whether it's true if we don't even know what would indicate that it is false? So you always have to have some kind of method by which, at least in principle, you could check for this thing being false. If there's no way to check whether it's false, then it's not a scientific claim because it cannot be proven through experiment. If you can't prove whether it's false, then you also can't do anything to test whether it is true. Okay, so what are some unfalsifiable, non-scientific claims? Take like the horoscopes, okay? I'm sorry to say it, guys, but if you believe in that stuff, you need to stop. It's just not rational and there's no scientific basis for it. But look, if a person says, look, I believe in the horoscope because my sign is very similar to my personality and the predictions kind of bear out truth, well, is there any way of falsifying the astrologist's claim? Does the astrologist say, look, don't take my word for it, conduct an experiment. And here's a controlled experiment with double-blind methodology, and it will show you that my claims are right. But if they're not, then the experiment will show that. No, there's no empirical data or studies that are conducted to try and verify these claims. They're just saying, take it as a given, and no, you can't disprove it. So if you cannot disprove it and it can't be subject to experiment, then it's not something that can be scientifically proven either, and therefore it's outside of the realm of science. Another example that's mentioned in the book. So Albert Einstein, his theory of relativity, he said, if this theory is correct, then here's one predicted effect that it will have. According to the theory, massive objects should have a gravitational effect on light because light has some particle-like properties. So that means that rays of light from behind a big massive object should be bent. And so if we have a solar eclipse, for example, then we should be able to see the occluded objects that are behind the sun as the light rays bend around the surface of the moon that's blocking it from our view. Okay. Now, he said, if my theory is not correct, then in the next case where there's a solar eclipse, observe these stars that are behind the moon that's blocking the sun's light. And if you can no longer see them, then that means that the refraction of light does not bend around the lunar surface. So, I mean, it's a complex example, but the basic picture is, he said, don't take my word for it, test it. And if you do a test and this does not happen, then I guess I'm wrong. Of course, when there was another solar eclipse, they observed the phenomena, and they were able to see objects that were otherwise obscured by the phenomenon of the eclipse. So it verified his hypothesis. But it had the ability to be falsified if a different result was shown. So that's what it means to be falsifiable, to give conditions under which the theory could be somehow disconfirmed. If there's no mechanism to disconfirm, then it's not a scientific claim because it cannot be verified through testing. Sigmund Freud, you guys maybe have heard, the famous father of psychoanalysis, father of modern psychology to some. He has some interesting ideas and he's had a huge impact, but he also had some weird unscientific stuff that was probably the product of him doing a lot of cocaine and other drugs. As an example, he says this stuff, that like if you're a little boy or girl growing up, you have all these proto-sexual attitudes. So he has all this like highly sexualized description of what's going on in the early stages of your infant development. As an example, he says that little boys have the Oedipus complex, meaning they have like a latent sexual attraction to the mother figure. And that's why he thought that in adult life, a man will sometimes find a partner that is somehow similar in temperament or personality or whatever appearance to the mother. And for women, he thought little girls have the Electra complex, which is just the same thing but parallel. They have a latent sexual attraction to the father figure, and that plays out in older life when they find a man that's similar to the dad. And he talks about penis envy that he thought little girls had and all kinds of other weird stuff, oral fixation and all that stuff. But here's the thing. He never said test this and that kind of experiment can confirm it. Or if it doesn't, here's what disconfirmation would look like. In fact, if you're saying to Freud, no, that is totally weird and off. I don't have any latent sexual attraction to my parents when I was a little child. He would say, oh, well, that's what you think, but you've suppressed it into your subconscious mind. So there's no way that you'll ever be able to prove that you don't have it. Then that's no longer a scientific claim because he's not giving us any experimental basis to confirm or disconfirm what he's saying. That's what it says here in the book. So I'll read it. It says, a hypothesis or explanation should be presented in a form that can be tested. Philosopher Karl Popper pointed out that no number of positive outcomes can confirm the theory, but a single counterexample does prove that it's false. Therefore, one of the main tasks of a scientist in testing a hypothesis is the search for negative falsifying instances. For example, the hypothesis that all swans are white was based on observation of hundreds of thousands of swans, every one of which was white. However, the hypothesis was falsifiable, since it would take only one non-white swan to prove it false, which happened when black swans were discovered in Australia. So, on the other hand, theories that can accommodate all challenges have a critical weakness because they cannot be tested for falsity. For example, Sigmund Freud's theories about the Oedipus complex fail the falsifiability criterion, since if a man claims that he does not have this complex, the Freudian would argue that he has repressed it into his unconscious. However, unconscious thoughts by their nature can't be tested, therefore there's no way of falsifying Freud's theory. Okay, so you have to have the ability in principle to demonstrate that the theory is false. Otherwise, you couldn't test it, and in that way, you can never even experimentally verify that it's true either. Okay. Cool. So hopefully that makes sense, guys. If not, you can ask me questions on it later, but let's go on. And we have one more quality of a good scientific hypothesis or theory to add here at the end. So the last one is just predictive power. Predictive power. So a good scientific theory can be used to accurately predict the occurrence of future events. Okay, good scientific theory can be used to accurately predict future events. So science gives us, in an interesting way, like knowledge of the future, because say, for example, you know how two chemical elements will react when they're combined with each other. If you know this because of your theoretical and scientific knowledge about the properties of these two chemicals, then it's not like a mystery or a surprise when you combine them together and you see the given reaction. Now, that result that was predicted by the theoretical understanding of these different elements, that gives us a reason to respect the theory, because the theory that tells us this will happen, then we observe it happening, so we should think that this theory is getting us to the truth, right? Because it makes predictions that then are realized in fact. Another example. You guys know about like lunar and solar eclipses. I mentioned them briefly just a moment ago. Well, say for example that the sun's light is blocked by the moon, and so we kind of have a big solar eclipse going on. When that happens, it doesn't take the world by surprise, at least not anymore. I mean, primitive people, prehistoric people, I'm sure they were pretty freaked out by it. But nowadays, we actually know down to the last detail the exact time and date when these things are going to happen. So you could go on Google right now and look up, like, when is the next time that we're going to have a full solar eclipse? And you can even see what parts of the Earth's surface would be the best places for viewing the eclipse, right? Now, when that event happens on the exact date that the scientific community has predicted according to the theories that they understand, that gives the fulfillment of the theory in the reality. And that tells us again that these people are not just playing guessing games and like having random hunches, but that these theories are quite correct to the real world that we are in. So predictive power adds credibility to a scientific theory. If it says that this is a thing that will happen based on the theoretical understanding we have, and then it does happen, the fulfillment of the predicted event is yet another basis of support for the scientific theory. When you see the weather report and it says bring an umbrella because there's a good chance of rain, 80% chance of rain on Friday, usually that's relatively accurate. I mean, of course, it's not 100% perfect when it comes to meteorology and the science of weather, but it's also not just a random guessing game where it's like maybe it'll rain, maybe it won't, who knows. With a high degree of accuracy, we're able to predict these things because of our knowledge of weather patterns and the physical forces that generate these weather outcomes. So to the extent that the weatherman's prediction is fulfilled in what we see, to the extent that the dates and times of eclipses and so forth occur exactly as predicted, this lets us know that the scientists that generated these theories and the theories themselves are believable, credible, and that they're not just way off base. Even something as simple as like the technology in your microwave, right? The fact that your microwave doesn't blow up, but it operates according to the same physical principles of electromagnetism that we understand. It shows you that the scientists that master this technology and that craft it for our use are developing them on the basis of theories that are true and accurate to the objective world. If the weather patterns were far different from what the common predicted outcome is, or if solar eclipses and lunar eclipses did not happen on the predicted dates, then we might start to wonder, are these theories just speculation and kind of just hunches that we shouldn't grant too much deference towards? But to the extent that predictive power is shown, it just means that it's a better and better theory or body of theories. Okay, so finally, the last thing I say here about our chapter 12 is just to know the difference between real science and pseudoscience. Pseudoscience is not good. So what is pseudoscience? The word pseudo means false. So in a certain way, the concept is just fake, false science. But to be a little more specific, pseudoscience is something that wants to appear to be scientific, but it's really not. So it is a body of explanations that, this is the textbook's wording, that masquerades as science, but it's not really science. Pseudoscience, and that's just like fake science. So a body of explanation, something that wants to appear like as some kind of field where expert, members of that field can deliver you real high-level information and knowledge. But no, take for example. So what are some examples of pseudoscience? We've got stuff like astrology, the astrological science. Palm reading, crystal ball gazing, tarot cards. Good one there, Yvonne. Numerology. Okay. And that's just, scratching the surface. There's a lot of others that we could also talk about. Divination with these divining rods and stuff. Psychic predictions, right? Psychics and all of that. Now, with all of these different pseudoscientific realms, you can tell that they're pseudoscientific because there's no kind of scientific experiments under controlled conditions that are generated to verify these things. They make claims that are not falsifiable, and oftentimes they use such vague and non-specific language that they could say that almost anything fulfills their so-called predictions. Take astrology, like the horoscopes. Try this one time. This is fun. So blur out the name of the astrological sign on a given chart and scramble them up, and then try to pick out which one you think actually corresponds to you. I guarantee you're going to have a hard time doing that because the predictions of all are stated in such generic language that there's some possible way for you to connect an event from your life to the given prediction there. Like, for example, there's no way that the astrologers will ever say you have falsified their prediction. Say that the prediction was this. Today will bring great things for you because you will see, you'll be visited by an old friend. An unexpected visitor will come. Okay, so you see the prediction and you're like, nobody came. I just stayed at home on quarantine all day. What are you talking about? But then, they might say, well, did you notice that little songbird that perched on your balcony? That's maybe the hidden message behind it. You had a little visitor and it was that wonderful little bird chirping as you woke up in the morning. So anything then gets counted as verification for the prediction. If nothing could ever be qualified as a falsification, then these are not scientific claims because there's no way of showing through any kind of result that they were false. Again, if something can't be falsified, then it cannot be tested either, and that means it's not scientific, because scientific things have to be tested for accuracy, confirmed or disconfirmed. Take the psychic predictions of Nostradamus, which some people believe in. This guy lived hundreds of years ago, and some people think that if you read his writings, they contain predictions of all kinds of world events that happened much later, like 9/11 or the rise of Nazi Germany or whatever. Okay, so what about his prediction that 9/11 would happen, so-called? Here's the passage that people are referring to. Fire of the center of the earth shall make an earthquake of the new city. Two great rocks shall long time war against each other, and after that they shall color red the fresh water. Okay, come on, do you really get 9/11 from that? There's something about an earthquake, a fire, two great rocks, and red water. But I mean, had 9/11 not happened, you could have attached this to almost any kind of warlike scenario where blood is in the water and there's some kind of fire that happens. So only on the vaguest and dimmest set of indirect associations could a person claim that this is like a legitimate prediction of something that happens in the future. And so let's just make sure that we're not fooled by pseudoscientific claims. There's a lot of people who are trying to make money on us by peddling false unscientific and pseudoscientific claims to us. In many cases, these people are trying to sell products, services, paywall, web hosting services, and all kinds of things. So as good critical thinkers, we should be wary about the information environment that we're operating in. It says, again, pseudoscience literally means fake science. To avoid falling for the empty promises of pseudoscience, we need to know how to critically evaluate the claims of pseudoscience. We should also be aware of how cognitive and social errors can distort our thinking and make us vulnerable to the lure of pseudoscience. A lot of times these are worldviews and stuff that tell us things we already want to hear, and so our confirmation bias makes us more susceptible to them. But remember, the world's not just about what you want or what you hope, it's about objective facts. So you've got to try your best to appreciate the objective facts, and in the end, you'll be better off for that reason. You know, if you have a psychic healer that's telling you just wishful thinking is going to get you through your cancer problem, and the scientific community says, no, you need to get chemo and radiation, you might really think twice about taking the comforting thought that this is not a huge issue that you have to have an invasive procedure to deal with, because that might make you feel good in the beginning, but meanwhile, you're not taking the proper actions to address an objective problem where there's scientific knowledge about how to deal with it. Okay, guys, so we've now finished with chapter 12, and that sets you guys all up for the quiz that's on Monday next week. So Monday, April 26th, next class, just as we've done before, I'll send you the quiz form right before class time, and you'll have until 2:15 to submit the answers back to me. And then we'll just continue from there. We'll start on chapter 9 next week on Wednesday. So until then, I guess I'll see you guys in a week, but we'll be in touch in between now and then for the quiz and other things. So is everything good? Let me know in this chat that everything's good and we're good to go. And then I'll close us off. Okay, thanks again, Yvonne, and for all your help and comments. Were really helpful. To everybody else, are you here? Is it all good? Just want to take a second. Okay, thanks, Danny. Thank you, Chelsea. Perfect, guys. Awesome. So have a good one, and be in touch. I'll see you soon. Okay, thanks.